No, okay, I think we can start. So welcome everyone to the third seminar of an optimal seminar series on optimization and learning for energy systems. My name is Vladimir Dvorkin, and I'll be your host for today. It's our pleasure to host Subhonmesh Bose, assistant professor in the Department of Electrical and Computer Engineering at the University of Illinois at Urbana-Champaign. His research focus on facilitating the integration of renewable energy resources and distributed energy resources into the grid using the methods from optimization, game theory and control. Before joining the University of Illinois, he was a postdoctoral fellow at the Atkinson Center for Sustainability at Cornell University. And prior to that, he received his master and PhD degrees from Caltech. This year, Subhonmesh Bose received a prestigious NSF Career Award, and he's been a co-recipient of Best Paper Awards at IEEE PES General Meetings in 2013 and 2019. And his research projects have been supported by National Science Foundation, Power System Engineering Research Center, Siebel Energy Institute, C3AI, and other sources. So thanks for joining us today. Please feel free to ask your questions, drop them in the chat as we go, or wait for a Q&A session at the end. And yes, I think I'm done. And Subhonmesh, please, the stage is yours.
Thank you, Vladimir, for first of all inviting me to give a talk at this seminar series. So today I'm going to talk about risk-sensitive market design for the power grid. This is mostly joint work with my students, Avinash Madhavan and Mariola Andrew. Mariola graduated recently at UIUC, and some part of it with my collaborators, Ye Guo, who is currently at the Tsinghua Berkeley Shenzhen Institute, and Lang Tong at Cornell. And for this work, I thank our sponsors, initially I2C-NER, then ISO New England through PSERC, and more recently, the NSF. Before I begin this talk, it's always a pleasure to talk to this group. And I was actually giving a talk on a completely different topic for the LIDS hosted workshop on COVID-19 a couple of weeks back. These are trying times for us. And I hope everyone attending here and otherwise and their loved ones are safe. Hope at some point we can have these discussions in person. Okay, so with that, let me begin. So if you think about electricity market operations, the cornerstone of electricity market operations is this so-called economic dispatch problem, right? Which essentially in its simplest abstraction looks as such, where you're trying to minimize some procurement costs of power, right? Subject to constraints pertaining to the assets that are connected to the grid. They must abide by certain constraints, right? And then the network itself imposes certain constraints, right? So this is in its simplest abstraction. But the story gets a little more complicated once you account for uncertainties. And there are sort of two kinds of uncertainties that I'm going to refer to. One are these discrete uncertainties, and then there are continuous uncertainties. So by discrete uncertainty, I mean a collection of what if components failure scenarios, right? So think about I mean, this is an engineering system, components can fail. And so you must, the power system cannot just stop working if one component fails. So the idea is to perform a dispatch or have a mechanism to guard against such discrete uncertainties, right? The second, the continuous uncertainty is due to this proliferation of resources like wind and solar, which sort of take values over a continuous, possibly a compact set. And think about wind and solar, they are uncertain, intermittent, and largely non-dispatchable. So one must account for this uncertainty in power system operation, right? Now, the story gets more complicated once you start considering another source of difficulties with these economic dispatch problems that arise due to non-convexities, right? Non-convexities either in power flow equations or even cost structures due to integral commitment decisions, etc. So in this talk, I'm going to completely sidestep the difficulties that arise due to non-convexity. So by that, I mean, I'll simplify my power flow equations to a nice linear power flow model. My PhD was actually in tackling non-convexities of power flow equations. So for this talk, let me sidestep that difficulty and only concentrate and focus on the difficulties that arise due to uncertainties. Okay. So when you think about uncertainty and in electricity market operations, one must therefore explicitly model the uncertainty and then have a way to dispatch against that uncertainty. So the view we take is that or we model these uncertainties through a risk measure, and more precisely, we choose this conditional value at risk measure, which is a coherent risk measure. To give an idea of what I mean by this is, think about a loss which is uncertain. So it may have, let's say, a probability distribution as such, right? Then essentially what a risk measure does is it processes this possibilities and their probabilities and maps it to a number. Right? So conditional value at risk is one such map with favorable properties. It essentially, for a loss with a continuous distribution, CVaR essentially what it does with a parameter alpha is it looks at the 1 minus alpha fraction of the worst case outcomes and takes its the expectation over that. So this is expected tail loss. Right? And if you set alpha to 0, this goes to the expected value of the random variable. While if you drive alpha towards 1, you are choosing something that is close to the worst case, or the essential supremum, to be precise. For losses with general distribution, CVaR is defined via this variational characterization. This is seminal work of Rockefeller and Gurdjieff. And this variational characterization, as we will see, really allows us to, we can take advantage of it in multiple ways. So CVaR, first of all, I'll in electricity market operations, what I will do is try to sort of motivate why it's useful to think about CVaR-sensitive formulations, right? So the formulation itself is important, why we want to look at electricity market operations with this measure. Then certain algorithms to be able to solve this, so custom designed algorithms that we would like to solve these sort of CVaR-sensitive optimization problems. And then finally, if you think about one of the important things about CVaR is that it retains convexity. It retains convexity of the underlying deterministic variant of the problem. So which implies that I can then take advantage of very mature duality theory of convex programming to be able to even try to attempt to define prices, right? So what we will see is that there are, in this talk itself, I'll take 3 different approaches of exploiting this variational characterization. In one case, I'll use it to reformulate the entire problem into one that is a deterministic one, a deterministic optimization problem. So I'll take the CVaR-sensitive problem and turn it into a deterministic optimization problem, and then try to design algorithms for it. Then in one, I'll take a stochastic approximation result that we have on sort of CVaR-sensitive problems. And in the third one, I'll sort of adopt a sample average approximation with data. So with that said, basically the setup of this talk is the following. That is, I'll first talk about handling discrete uncertainties through conditional value at risk, and sort of reformulate the problem and show a particular way to sort of we've been working on a particular algorithm to solve it. The second one is sort of a particular problem that arises in power system operations. We'll try to essentially design some results on stochastic approximation. So basically the goal would be, I'll take the problem in power system that arises, abstract it out to a sort of a generic optimization problem, and provide a particular mechanism to solve it. And we'll share some results that we've got recently. And then finally, I'll attempt to define prices. This is very recent work. So I'll just attempt to define prices, and there the computations will all proceed via sample average approximation. Okay, so let me jump right into the first part, handling discrete uncertainty. And as we all know, power system must continue to function even after possible component failures. At least there are these N-1 security criterions, for example, which deems the power system must function properly even if one component out of all these components fail. So think about transmission lines failing. If one transmission line fails, one can take a very conservative approach of this, what is called preventive security, say that, or demand that the dispatch that you compute must still remain feasible within the network, even if the network constraints change after one transmission line failing, right? Clearly, this is fairly conservative, right? You can take corrective actions. You can think about even possibly shedding load. You may also add some recourse costs and even penalize that, and so on, right? So these have been proposed. Corrective schedules have been proposed. In our work, what we try to propose is this following conditional value at risk sensitive objective, where what is random here? It's the recourse cost. The recourse cost only arises if there is a particular contingency that arises, right? So these, under a failure scenario, there is a recourse cost, and that is random. So you can then define this conditional value at risk with a parameter alpha. Now, why do I want to do this, right? So let's look at this particular example where if you move your eye from the right to the left, as I'm varying alpha in a way that from the right to the left, here it's more risk neutral, and towards the left, it's more risk averse. Right? As you go towards the left, the nominal dispatch cost increases as you become more risk averse, but at the same time, the amount of load shed in the system largely decreases, right? And so this essentially is so as you get more risk averse, you are okay with higher nominal dispatch costs, because it buys you more reliability, because you wouldn't have to shed load otherwise. But as you go towards the other end, you are essentially okay with some load being shed, but you are really reducing your dispatch cost, nominal dispatch cost, right? So this is a way for a system operator to trade off between procurement costs and reliability of power delivery. And this kind of a graph arises mainly due to the fact that in power system operation, whenever you think about shedding load, you penalize the objective through a value of lost load, and value of lost load is typically higher than generation or recourse costs. And hence, this kind of a trade-off arises, right? Okay, so till now I've given a formulation. So if I take that formulation and then utilize that variational characterization, and with all the power flow equations being nicely linear, you can reformulate this into a linear program. Well, then one might think linear programs are easy. Let's solve this, right? But let's look at the size of this linear program for a second, right? If you look at, let's say, just the base economic dispatch and the various different security constrained variants of this problem over just a 2300 odd bus node network, this Polish network, you see that the economic dispatch problem, the ED problem, is fairly small, right? I mean, I can solve it on my laptop fairly easily. But once you go to the corrective and the risk sched version, especially the risk sched, the number of variables and the number of constraints is enormous, right? So the scalability of the algorithm really comes into, I mean, you need to, even though this is a linear program, you need to be able to solve it in a scalable fashion. So what we have been investigating is a particular algorithm to solve these kinds of very large linear programs where it admits the following form. Think about X naught being all the variables associated with the nominal dispatch and XK as the variables that are associated with the kth contingency, right? Then you can rewrite this program as follows. It's linear in X naught and XKs. There are some constraint over the nominal dispatch, and there are constraints. These couple the nominal dispatch and what happens in the kth contingency, right? So this is the nature of the linear program that we want to solve scalably, okay? One can take the route of pre-filtering contingencies. Here, what we've been investigating is a way to parallelize this computation to come up with faster algorithms. So the way we have designed this particular algorithm and what we are interested in looking at is this, what is called what we have termed as the critical region exploration algorithm. There is a very mature theory of multi-parametric linear programming. This sort of the MPC literature has provided us with a lot of very interesting results. So we sort of take advantage of that. And
sorry, could I just add a clarifying question on your formulation?
Yes.
So this is economic dispatch. We are ignoring any unit commitment type of decisions.
Yes. Currently, there is no unit commitment here. This is only the SCED problem.
Okay.
Yes. But you are exactly right. If I were to use this in a day-ahead market context, there would be commitment variables on top of this, right? Okay, so in the multi-parametric linear program, what I can, taking advantage of that, so let me rewrite this object where I'm essentially taking out everything that pertains to xk and sort of nicely packaging it into this jk star of x naught, right? So this jk star of x naught is the solution of another linear program that is parameterized by x naught, right? Now, what you can show is that this jk star x naught is piecewise affine and convex, right? And moreover, the pieces over which the cost is affine, so it's piecewise affine and convex, but the pieces over which it is affine, that defines a polyhedral partition of this set x naught. Right. So what do I mean by this? This is sort of a mouthful. Let's try to parse this. So think about just two J1 star and J2 star. They are essentially, you can then partition x naught into two polyhedral regions. Over each of these, call them critical regions. Over each of these critical regions, the cost is affine. So it's some affine function here and some other affine function here. But together, it forms a piecewise affine convex function of x naught. So J2 star will have similar critical regions. Now, if you then sort of, when you take the J1 star plus J2 star, right, that would define essentially, again, it would be piecewise affine and convex, but its description will be affine over sort of these sets that are intersection of the polyhedral partitions that we get from the two different subproblems, right? So now I have a piecewise affine convex function, right? How do I optimize over that? Now, one way to do that is what we have come up with is this critical region exploration algorithm, which is you start from a point, you optimize over just that affine description over just that piece, okay? Suppose you get to that corner, then now I would like to verify whether this point is optimal. Now, how do we verify something is optimal? If I have a piecewise affine convex function, 0 belongs to the subdifferential set, right? Now here I have only explored really just this one affine piece. So I don't really know whether what the subdifferential set fully looks like at the moment, right? Because I have not really probed what the function is at the different other places yet, right? So I have only found out the affine cost description here and the critical region here, optimized over it, got to this point. But I have at least one subgradient, right? Well, you check whether that subgradient is 0 or not. If it's not, then you push out to a neighboring critical region, right? Then you optimize over this piece, right? With the affine description of the cost functions and this critical region description, right? You may return to the same point. But now again, you check whether the optimality condition is verified. Now, here, the subdifferential set, well, you may not know all of the subdifferential set, but you have a little more information at this point, right? Because you had explored this, so you knew what the affine description is here, what the affine description of the cost is here. So then you know a little more about the subdifferential set at this moment. So you can check for it again. But if it is not true, you move ahead and then proceed to explore another critical region. Now, you should do this in a way that you do not ever return back to a critical region that you have already explored. Otherwise, the algorithm can cycle. And once you do that, you keep going with this because the number of critical regions is finite. One can imagine that you would be able to prove this. That is, CRE algorithm converges to the optimal solution of this risk-sensitive SCED problem in finitely many iterations. But finitely many, again, we don't have a complexity bound on this. All we say is that it's finitely many. right? And the algorithm is described here. We actually came up with this algorithm in a very different context for robust timeline scheduling in multi-area power system. This is the work with Ye Guo and Lang Tong, and it's published in Transactions on Power Systems. But we quickly realized that it is really just a way to sort of parallelize computation of large linear programs. Now, there are very well-established algorithms like Bender's decomposition to tackle the same problem, right? And so if you think about what are the parallels and differences between CRE and Bender's decomposition, what CRE does, think about a piecewise linear convex scalar function, right? So just a very simple function of this form. What CRE is doing is basically exploring piece by piece and trying to certify optimality of the point that it's finding, right? While Bender's decomposition, you first find sort of these cuts, right? So the dual cuts. And so you think this is your function at the moment, and then you optimize over it. Well, then you find a new point, and then you add another cut. So it's creating this global picture. Once you have this, then you again add this cut perhaps, and then you find that this point, then you find another cut here, and now you can certify optimality of this point, right? So Bender's is basically creating a global picture of the function, while CRE is locally exploring. Now this picture sort of motivates the parallels and differences between these two algorithms, and we are in the process of formalizing this these parallels and differences. And moreover, one can now think about taking things that are good in both these algorithms and perhaps coming up with a hybrid one. So this is something that we are working on. Our initial paper on this was published in PES General Meeting on utilizing CRE for this risk sched problem. But we are currently working on something where we take advantage of the pros of both CRE and Bender's and sort of implementing it. And this is something we're exploring with our collaborators at Los Alamos National Laboratory. So far, what I've done is essentially taken this discrete uncertainty, modeled a risk-sensitive security constrained economic dispatch problem, and sort of posed this question that this is actually a very large linear program. And so we've been investigating this custom designed algorithm to be able to solve these. Now we are trying to explore and understand what their parallels and differences are with sort of the well-known Bender's decomposition. So that's where we are at with this. Okay. So that sort of finishes the first part of the talk. Let me move on to the second one. The second one is where we start looking at the other kind of uncertainty, where it's risk-sensitive economic dispatch with uncertain wind. So here I'm going to happily sidestep the difficulties of security constraints due to different possible component failures, and only look at the question with wind, right? So here, if you're looking at, let's say that the wind is uncertain, then how does it complicate the story of our very simplified, oversimplified perhaps, this deterministic economic dispatch problem? Well, you can think about wind and club it with the demand, subtract it out and call it the net demand, right? And then the generation must sort of then account for how it would respond to possible forecast errors in that wind forecast, right? Now, with that, so now you need a way for the particular generator to respond. Here we resort to these well understood or well studied linear decision rules. And what we essentially do is, with that linear decision rule, we formulate a CVaR penalized, CVaR constrained form of solving the risk-sensitive economic dispatch problem with uncertain wind. And it takes the following form. Now, this formulation it's very, there are similar formulations in the literature, I must acknowledge, by Summers et al. And so what we do is we now think about, how do we solve this kind of an optimization problem? Now, if you think about this kind of an optimization problem, and one way to do it is, again, can I reformulate this into something? This is stochastic optimization, right? Because it has this risk measure in the formulation itself. The other way to think about in this kind of so one way to do it is to reformulate the stochastic optimization as an instance of a deterministic optimization problem. The other way to think about it is with the data, can you solve this, right? And there are sort of two sort of ways one can approach this. One is sort of stochastic approximation, and another is sample average approximation, right? So stochastic approximation, the idea is you sample and you move the iterates, right? And in sample average approximation, you first take a set of samples and then sort of somehow use that to formulate a problem with it, right? Roughly speaking, take all the expectations if there are, and you replace them with empirical means, right? So let me first talk about some of the results that we've obtained in analyzing a stochastic approximation for these kinds of problems. Now, take my word for it for now that we have this equality constraint, but it is a simple enough equality constraint that you can get rid of and pose that problem as an instance of this particular optimization problem. So you're minimizing the CVaR alpha of some function subject to CVaR beta I of this function. Okay. Now, these kinds of optimization problems, as you might imagine, are extremely, I mean, this is extremely expressive, right? So let's think about what beta I's model, right? If you take beta I to 0, what you're essentially saying is impose this constraint on average, right? If I say that beta I is, if I drive beta I to something close to 1, I'm saying the essential supremum of this is less than or equal to 0, which is essentially saying roughly enforce the constraint in an almost sure fashion, right? So this kind of an optimization problem is extremely expressive, and a similar story holds for alpha as well, right? If alpha is just 0, you are essentially taking the expectation of this. And if you are driving alpha close to 1, the modeler essentially wants to express that they are averse to very large uncertain costs, right? So now for these kinds of, these sort of CVaR penalized, CVaR constrained optimization problems, as I was trying to argue, is that these are extremely expressive. So it makes sense to think about how do we solve these kinds of problems with data, right? And these are also very well, these kind of conditional value at risk sensitive constraints, they are intimately related to chance constraints. This is very well known, is that these kinds of constraint enforcement is in fact a convex inner approximation of a chance constraint. So chance constraint seeks to bound the probability of violation. Conditional value at risk not only does that, but in addition, it tries to control the extent of the violation. So it's extent plus the probability, right? Now, in what follows, I'm going to describe sort of a stochastic approximation, or more precisely, a stochastic primal-dual algorithm to solve these kinds of problems, right? So this part of the talk, it's more about just the analysis of this stochastic approximation of this kind of an optimization problem. So let's first, the roadmap is the following. We first just investigate the simplest case, that is alpha and beta equal to 0. If you set alpha and beta equal to 0, the PCVaR, that problem, it reduces to just you're minimizing the expected value subject to expected violation less than or equal to 0. So this is just the simplest version of this. And we develop essentially a stochastic primal-dual algorithm. It's fairly simple. This is classic primal-dual, but with a slight twist. Okay, so what is that twist? So essentially, it's again, this is the primal update. This you sample, you update your primal. But in the dual update, typically in the algorithms you find they use the same sample to update the dual. We don't do that. We sample again. So this doubles the iteration, the sample complexity to that of the iteration complexity. But why do we do that? I'll come to that, and what are the advantages of that? Okay. So currently what we have, so what I have described is just a mechanism to solve this PE, which is the expected version rather than the conditional value at risk sensitive version. Now you use the variational characterization of CVaR per Rockefeller and Uryasev, and then you reformulate the PCVAR into a form that is exactly, that looks like PE. And then you solve that reformulation using the same stochastic primal-dual algorithm. So that's basically the roadmap, right? So let me just quickly describe the nature of the result. So with these gamma k's, if you think about these gamma k's are essentially the step sizes. So with gamma k's, the step sizes, what we are able to bound is the expected suboptimality and expected constraint violation with this object. Now, this object, if you take the following kind of step size, you fix the total number of iterations you want to run, capital K. Then you take a constant step size of gamma over square root of capital K. So this is not a decaying step size. It's a constant step size, but with this predefined number of iterations. Then what you get is the convergence guarantee that you get gives you this 1 over square root capital K guarantee. Now, this is order optimal in the sense that if you look at the problem PE, remove all the constraints, this is a, and we don't assume capital F to be smooth. So for non-smooth deterministic convex optimization, 1 over square root capital K is the best you can get per Nesterov's seminal result. So this is essentially order optimal, right? Now, why do we do that extra sample? Essentially, what we are able to show in these kinds of optimization, these kinds of algorithms, if you look at the classical analysis, it typically requires the dual variables to be bounded. So you either assume a bound on it or you project back onto the set, or you have to intelligently come up with ways to sequentially bound it. Our proof technique is such that we define the dissipation inequality. They're very classical primal-dual proofs. But after the dissipation inequality, we utilize the inequality to compute a bound on the dual variable growth, rather than explicitly having to impose it. And then we utilize the inequality to derive the bounds on suboptimality and constraint violation. So this proof is very closely related to classical proofs in the literature, but we are able to circumvent this, this important limitation of having to know a dual bound. So with that particular algorithm, what we are then able to do is the following. So suppose you give me a tolerance, your tolerance of how closely you want to approximate, you give me an epsilon, then I would like to find out my eta, which, I would like to find my step size. I would like to optimize my step size in order to minimize the total number of iterations, and you can actually compute this. What the iteration complexity that is required to get you to within a epsilon tolerance, right? Now, once we try to apply this to PCVAR, right? As I said, you take PCVAR, you utilize Rockefeller and Uryasev's variational characterization, reformulate that as an example of this problem PE, right? This problem PE, and then you apply the stochastic primal-dual method to that, right? Now, because I have this case, what are the nature of the guarantees? What we are able to give, again, it's 1 over square root K for the CVaR constraint, CVaR penalized optimization. And now your constants, if you look at what the constants are here, this constant depends on the risk parameters, alpha and beta. Now I also know how to optimize my step size, right? So I can optimize my step size to get an optimized iteration complexity. Great. Now, if I have the iteration complexity, now I can find K star of alpha comma beta. And I can study growth of how much my iteration count grows as a function of my risk parameters. Now, this is something that we did because very inspired by the results of Campi, Calafiore, and Garati for chance constraint problems, where essentially this is the idea, right? You give me a risk tolerance, and I will tell you how how many samples you need. Now, if you think about the CVaR constraint problem, where this is a stochastic approximation, you sample and you move, you sample and you move your iterates. But if you think about it, conditional value at risk two, even though we never actually evaluate CVaR of any of the points at any of the points, the functions, yet if you increase a risk tolerance, you are essentially having to look a little more into the tail of the distribution. So naturally you will need more samples. So that sort of makes sense from even without doing all this analysis. And that's what even shows up. If you take some example problem and you run this, yes, K star in fact grows with alpha and beta. You can even prove it. As you go close to, so let's take a very simple example where alpha is going close to 1. So what I'm doing is taking this risk parameter to as close as 1 as possible. Then it starts growing as such, 1 over epsilon square 1 minus alpha whole square. So now if you think about it, if alpha is very close to 1, you are trying to solve almost a robust optimization problem using samples. No wonder that the sample complexity blows up, because you're trying to, as I said, trying to essentially solve almost a robust optimization problem with samples. It needs to see everything. And so the number of samples is essentially twice the number of iterations. That also goes to infinity. Now we've tried this on a very simple example. For example, I mean, we've run this for multiple examples. This is the one we report in our paper. Is this very simple example where the randomness is in omega. It comes from a beta distribution. Now, essentially, to evaluate, think about it, evaluating this requires me to compute the CVaR, right? So here, what we have done is we've taken 1 million samples. And using those 1 million samples, we have computed the objective function and the constraint here. And that is sort of shown here. And you can verify this is the optimal. And once you run the algorithm, the stochastic primal-dual algorithm on the reformulation of the CVaR-sensitive problem, you get sort of this behavior where it seems to converge. But mind you, the guarantee that we get, let's look at the guarantee for a second. We guarantee that the expectation, so if you run this stochastic approximation algorithm multiple times, you will see that the average of those should satisfy this, right? It's not a sample path guarantee. Yet what you see, I mean, even though the analysis shows a weaker sort of notion of convergence, it's only saying things in expectation. It doesn't say anything about a sample path. But in our experiments, we've never come across one where it doesn't satisfy these bounds. So the bound here is epsilon is somewhere here. It's, if I recall correctly, it's 5 times 10 to the minus 3. It gets there even way before what we define as the K star, right? So this is sort of the downside of optimizing. We've essentially taken an upper bound on this, right? Think about where this bound came from, where K star is computed from. We've computed an upper bound and optimized the upper bound to find the number of iterations. So typically when you try to do that and you're optimizing an upper bound, that may not be tight, right? By the way, the graph is a little more jittery here. And the reason is the following. We've only taken, when we are evaluating the capital F, this function fully here, when we're evaluating it, that evaluation of the CVaR with million samples, if you, it's essentially, if you wanted a very smooth graph, 1 million is not enough. Once you want, given that the log scale of the plot, this would be a lot more smooth if, rather than taking 1 million samples, if you took perhaps 10 million or 1 billion samples here. Makes sense? So coming back to what we've sort of done is we've taken the problem in power systems, which is sort of this CVaR-sensitive problem. We cast it as an example of this sort of generic CVaR penalized CVaR constrained optimization problem, and analyzed a stochastic primal-dual algorithm. And what we have essentially been able to show by optimizing step sizes and so on, at least our optimized iteration count grows with this risk parameters. It sort of shows this, what I call as the computational cost of the preference for robustness, right? So we are in that domain where if you formulate a particular problem, I can demand as much risk aversion. I can demand as much robustness as I want, but we must account for the fact that the algorithm might also take longer to converge there. So essentially, the modeling itself no longer is devoid of, or you can't just do modeling for an application domain without taking into consideration what it takes to solve it. right? Our paper is still under review, but you can find the archive preprint here. It's given here. Okay, so that sort of ends the second part of my talk, and I want to end with something that is very recent, but just to sort of give a sort of a very short, just highlighting this particular piece of work that we've just started doing. A lot more needs to be done in this space. So there have been results by sort of motivated by Yuri Vorkin's work on defining prices from a chance-constrained electricity market. We wanted to think, is there a parallel with conditional value at risk-sensitive market design? Can you come up with prices, right? Market design is incomplete unless you you formulate the problem, you define algorithms, but you also have to compensate market participants, right? So there has to be some notion of prices and payments and so on, right? So we looked at this problem and we simplified it with some assumptions. So the first one was we took alpha to be 0, so it's an expected value. And in fact, if you assume that the forecast errors, the expectation is 0, then it sort of simplifies. And you also deem that the nominal dispatch clears with the expected wind. So then this formulation simplifies a little bit to this particular optimization problem. Again, you have sort of CVaR-sensitive constraints, but then you reformulate it using the variational characterization of Rockefeller and Uryasev, and you get constraints like this, where there are expectations here, right? Now you can define Lagrange multipliers with respect to these constraints, right? And then we define a vector of risk-sensitive locational marginal prices as such. Here, I mean, this definition exactly mirrors that of a classical LMP, where there is a price due to sort of balancing demand and supply, and then there is a congestion component. But here, the congestion component, it is no longer dependent on just the nominal dispatch, but the dispatch across the scenarios, right? And you can show certain things. For example, like you can, as you take the, if the line limits are not binding, then this, it becomes uniform, right? And then again, this reduces to the classical LMPs if the wind variance disappears. So we are trying to essentially generalize LMPs to its risk-sensitive variant. You can define certain payments using these prices. In the interest of time, let me skip that. And you are a very important consideration in market design when you're trying to define prices is the mechanism revenue adequate? In this case, we are not able to show that it is always revenue adequate, but we are able to actually analyze the merchandising surplus. And it turns out, so for classical LMPs, its merchandising surplus is greater than or equal to mu transpose F. That's sort of what holds for classical LMPs. And that's why you can say it's greater than or equal to 0. But in this case, what we are able to show that it's mu transpose F plus a risk-dependent term. And we cannot get rid of the risk-dependent term. And what we are essentially, and this risk-dependent term, again, if the wind variance goes to 0, this goes to 0 and so on. But there is a problem with the fact that we can't guarantee revenue adequacy across all scenarios. Right.
One quick question on that. So yes, you need to come out also with values for the PIs that you use in order to weight your expected value, right? The
PIs?
The probabilities attached to each one of these.
Yes. I mean, so if you have an expectation here, right? Expectation is, I mean, that is with respect to some distribution. Now, there are lots of problems when you try to define a market mechanism with expectations, right? So for example, what is this distribution? Who knows this distribution? So in this work, we are sort of thinking about, or any of these kinds of markets, the way we are thinking about it is ISO utilizes perhaps a third party to get a distribution, and that is the distribution it utilizes to define all the dispatches. So that distribution is implicit in this definition, right? Okay. Now, how do you compute these dispatch and prices? The way we are thinking here is let's take samples, capital N samples, and replace the expectation with empirical mean over N samples, and then calculate the Lagrange multipliers and then compute the prices from there. Now, once we did some simulations, and it seems that these prices are converging somewhere. And so we are trying to analyze, again, this is very preliminary work. We just formulated it and sort of gotten some empirical results. We're trying to analyze and show that these, in fact, will converge to the Lagrange multipliers of the sample average base prices will converge to the true prices coming from this optimization problem. So we haven't shown this yet, but we are in the process of hopefully getting there. Okay, so let me sort of end on that note. So what I've shown here, if you look at these sort of the three things that I talked about, the third one in much more short, just summarizing it as compared to the first two, what I've essentially been looking at is two kinds of uncertainties, right? Discrete, continuous, and took them sort of separately, and then looking at sort of formulations and then algorithms for these two. And in the continuous world, I'm trying to think about pricing, right? Now, once you add these two, that's a whole another set of problems. The scalability challenge is fairly large, right? Because you now have contingencies as well as wind. And that's the true problem that the power system faces. So algorithmic challenges remain, pricing challenges remain. And I happily said, let's not deal with non-convexity in this talk. But if you are in the control room of a system operator, you don't have that luxury, right? You'll have to tackle somehow the non-convexity of power flow equations and even the cost structures. So if you were to use this in the context of the day-ahead market, to augment all these formulations with unit commitment, and then also think about pricing in that environment, right? So needless to say that there are lots of problems in this domain that we are eager to solve. And so it sort of suffices to say that this will keep us busy for the next few years. Most of this work that I presented is by my students, Avinash and Mariola. I'm really the transmitter of information here, and some of it with Ye and Lang. And I thank again our sponsors. So there are lots of future directions and lots of work to be done. Essentially the idea is, can we augment the formulations, the algorithms, the pricing, and more precisely the market design that was largely deterministic in nature, that sufficed for power system operation till now? Can we take a fresh look at this in the context of uncertainty, and rather than taking sort of an extreme view, either it's the canonical, stochastic, or average case, or the completely robust or the worst case, can we take somewhat of a middle ground through this risk-sensitive market design? With that, I'll end the talk. Thank you.
Thank you. So it's time for Q&A. So please feel free to put your questions in the chat or unmute yourself and just ask it directly. Maybe I can just warm up this part. To start with, in the first part of your talk, you were comparing critical region exploration algorithm with a Bender's decomposition, and we did see some parallels that shared between the two algorithms. But what we know about Bender's decomposition is that we always increase computational burden of the master problem every time we add the cut, right, to the algorithm. And I'm very curious if it's the same problem with the critical region exploration algorithm.
Very good question. It's a very good question. So as you're adding more and more dual cuts, you are increasing the complexity of the master, right, in Bender's. But critical region exploration, the master problem itself is fairly large. And the reason is the following. Think about what the master problem solves. It goes into each subproblem first, asks the subproblems to identify the critical regions over which the affine description of the cost is valid, right? Then it returns these two pieces of information to the master. So the master now has to also impose these constraints of the critical regions itself. And that's fairly large. And that is where sort of the difficulty has been to, even through lazy constraint generation, it can be slow. Even though Bender's cut is increasing the number, but we typically don't see that it's going to the same number of constraints as CRE's each master problem would have to solve. But one can take advantage of this. That is, when you think about Bender's cut, how is Bender's cut being solved? At the new point, just solve the optimization problem, the subproblem, right? Now, rather than doing that, think about if I already calculated the critical region, I know for a fact when I need to recompute or when I don't need to. And typically the numbers, so that you can really reduce the number of subproblems that you need to recompute. So we are trying to take advantage of both of these worlds and trying to combine them to get an algorithm that is hopefully faster than both.
Yeah. Makes sense. Thanks.
Can I ask one question, Vladimir?
Please go ahead.
Yeah. Thank you, first of all, for the very interesting talk. I had one question regarding your model with market clearing, including CVaR. And, my question is the following. I mean, what is, how you would interpret CVaR in that context? I mean, the parameters of CVaR, like alpha, for example, they should be defined, I assume, by the market operator in that case.
System operator.
Yeah, system operator. But how do we make sure that all the market participants actually agree and they have the same risk aversion appetite, risk aversion level?
So this is an extremely interesting question. I've been struggling with thinking about what is the right way to motivate this in the fall. And let's think about it in the following nature. If you have a line flow limit, right? Now you can say that the line flow limit is, typically these limits come from thermal considerations, right? So one can think about, well, do you relax it for a bit or don't you relax it for a bit? And so what you are essentially, the CVaR parameter for that particular constraint would give you is saying that, well, it is okay to violate by this much for this much probability, right? So the extent of the violation and the probabilities of the violation. So that is more, if you're thinking about line capacity constraints and defining a particular parameter, there it is more the system operator's consideration of what is okay for the network, right?
I agree. I mean, I totally agree with you. And for me, it's intuitively much easier to understand this concept when it comes to charge constraints. So when you say that, okay, as a system operator, I want to make sure that 95% of with 95% probability or 99% probability, whatever, I won't violate the thermal capacity of a line. But then translating that into monetary values and adding it to the objective function of the market clearing problem, it's a bit more it is harder to interpret. Right?
So two things to say here. One is that when you're saying chance constraint, so think about, you're saying 95% of the time it will not violate, right? For the 5% of the time, you don't have any handle on how much that violation is. But typically in case of at least when it comes to line capacity constraints, that is sort of, if you look at even the first formulation that I did with the discrete uncertainty, that is in fact what is done. That is, you relax the line constraints. If a contingency happens, you relax the line constraints for a bit. And it's because these are thermal in nature, relaxing constraints for a while is okay on certain things, right? For a while. Again, you bring it back. So this notion of dynamic line rating, right? Now, in terms of the interpretation in the market framework, I agree with you, but that sort of a problem will remain with any kind of a stochastic sort of setting if you do it for the forward market. In the forward market, this is where by the way, whatever I was saying in terms of defining where you think about risk-sensitive market design, this is in the forward market, right? So whenever you think about that, do you want to impose this across all scenarios? That's one way to do it. One way to do it is average. The other way to do it is you don't even consider any uncertainty at all. You just take a point forecast and go forward with that as your definition. But then you have to sort of completely take into account the forecast errors in real time. So the commitment decisions and etc. that you make at the forward, they don't reflect the fact that you can get hit in terms of uncertainty during real-time operations. So I don't think the cleanliness, the clarity that comes with the deterministic optimization style setting that can be fully translated in the stochastic setting. You have to make the best out of what is available. You either have to take into, you can say that we don't want to take into account any uncertainty in forecast errors, etc. We'll take it in consideration just in real time. That's one way to go about it. The other way to go about it is explicitly model it and somehow price it. The reason we have chosen conditional value at risk is it retains convexity, as opposed to chance constraints. Chance constraints also, I mean, under certain conditions and certain distributions, it still remains convex, but not for arbitrary distributions. So CVaR sort of maintains that. And on top of it, the way I see it is that this idea of not just the probability of violation, but the extent of the violation has also been taken into account. It's sort of, and these are actually more conservative than chance constraints. So that's why I feel that these market formulations, at least for the forward market, makes more sense.
Yeah, thank you very much.
You're welcome.
So we also have a question in the chat. So Kevin Kircher asks, could you tell a bit more about the recourse model used in the two-stage security constraint economic dispatch? Does it model the ISO's response to both continuous uncertainty, like from wind, and discrete uncertainty, like line failure?
I mean, this particular slide that is currently shared will answer your question. No, we don't. We do it separately at the moment, right? The discrete is here and the continuous is here. But as I said, as a system operator doesn't have the luxury of only dealing with one and not the other. So yes, we are going towards that, and a lot more work needs to be done. Definitely, and that's where the scalability challenge really lies, if you think about it, right? So think about 5 or 10 contingencies. And if I knew roughly what the demand is going to look like on these, I can say for sure, this is the bad contingency, and those are roughly the good contingencies. So you can even do some pre-filtering fairly easily, right? But once you complicate it with the wind, so in each contingency, there is also uncertainty in the demands. Now it's not so clear. It's not so clear which one you will prune randomly, right? So this leads to a gigantic problem. The scalability challenge is quite real. And so I'm interested in thinking about this. I don't have an answer for you. I haven't yet modeled it. Short answer to your question, but the long answer is I'm really curious how to get to that level of where we can actually design this. That is, it's both discrete and continuous uncertainty. Formulate the question, define algorithms to be able to scalably solve this in meaningful times, right? And then do pricing based on that.
Okay, I think we can afford one more question, and then we will wrap up. Actually been very efficient with the time. We made it 1 hour sharp, so which is a record so far. Thanks a lot for being so efficient. So I think that yeah, it's time for us to wrap up. Let's thank Subhonmesh again for this wonderful talk and for your questions. The recording will be available on our YouTube channel, and we will get back to you in 2 weeks with our next speaker, talking about managing flexibility of data centers. Yes. Thank you, everyone.